Godt. Jeg tror vi begynder nu her. Først og fremmest velkommen til dagens webinar. Det skal jo handle om det her nye modul til FEM-Design, 3D Bridge hedder det, som er helt nyt, noget vi har lavet i forbindelse med den nye version af FEM-Design, FEM-Design 23, der kom nu her i februar. Og det er jo nogle gange, der skal man kende sine egne begrænsninger, og det kender jeg her. Det er derfor, jeg har fået hjælp. Jeg ved absolut ingenting om broer og hvordan man designer broer. Så derfor så har jeg fået hjælp af min kyndige kollega Shaho. Shaho han sidder på vores kontor i Sverige og taler svensk, og derfor så har vi valgt at holde webinaret i dag på engelsk, bare lige for at imødekomme alle de sprogbarrierer, der nu måtte være. Vi bruger som altid den her GoToWebinar platform til webinaret i dag. Men vi har lidt nye folk med den her gang, som jeg ikke ser så tit i hvert fald. Sikkert også på grund af emnet. Så det er super fedt. Men derfor så vil jeg lige starte med lige at vise den her kontrolpanel, som I formentlig alle sammen ser ude i højre side af skærmen. I kan skjule det, hvis det er træls og fylder for meget, ved at trykke på knappen her. I kan altså få det vist igen, bare lige ved at trykke på den samme knap. Det er bare så det ikke optager pladsen, og I ikke kan se det, der foregår. Har I brug for at stille nogle spørgsmål, så kan I gøre det i den her questions-fane, hvor jeg vil forsøge at svare på så mange spørgsmål som muligt undervejs, ved at skrive tilbage til jer. Og så laver vi også til sidst en Q&A session, hvor vi nok lige skal tage de spørgsmål op, som jeg ikke lige har fået svaret på. Dem vi kan nå i hvert fald, og så vil Shaho forsøge at svare bedst muligt. Jeg skal lige sige, som jeg nævnte, Shaho han er fra Sverige, og er derfor mest bekendt med de nationale regler, der er i Sverige. Programmet er selvfølgelig lavet til Danmark også, og Shaho har brugt de sidste par dage på at lige sætte sig lidt ind i og læse det danske nationale annex. Men der kan altså være ting, der lige smutter undervejs, som er nogle værdier, vi måske kender mere fra Sverige frem for Danmark. Men det skulle der altså være mulighed for at tage højde for. Og ellers så stiller I selvfølgelig bare spørgsmålene, så skal vi nok forsøge at kigge på det også. Det var sådan set alt herfra, så Shaho, stage is yours.
Tack så mycket Anders. Vi ska testa om jag kan dela min skärm.
Yes.
Så där. Hej på er. Jag kommer inte köra på svenska, men jag vill bara säga hej. Jag önskar att jag kunde säga hej på danska, men det blir på svenska. But I will continue in English. And thank you for inviting me today, Anders. You see my screen, right?
Yes.
Perfect. I'll just make it a clean view so you don't see all the garbage. Perfect. So like Anders mentioned, I've looked at the Danish National Annex for Bridges. Of course, I've not worked with it, and my interpretations I did yesterday can have been faulty. So during today's webinar, if you have any questions or if you notice anything regarding the Danish national dependent parameters, please make a shout out in the questions or chat, and we can adjust it so it's suitable for you as well. But it will be quite briefly in the beginning, general Eurocode load models, and then we will look at some real case studies. And if you want to look at something particular, please you can write it in the chat already, and then we can try to adjust it later on. Okay, so briefly about myself, working in StruSoft Sweden, and I've previously been working as a bridge engineer with FEM-Design, but that was quite many years ago. FEM-Design 23, we launched 2 new modules. One was the 3D bridge, and the other one is a plastic analysis module. I know Casper, a Danish colleague of us, have been hosting some Danish webinars, so if you're interested in those, please have a look at them. But of course, many other new features. One of my favorites, the result visualization. So converting the shell internal forces to a beam kind of result, which is very easy to interpret. But the 3D bridge module, I will speak maybe for 20 minutes, and then we will look at some real case studies of it. What it is, what you can do with it, theory, and how you can use it. So what is it? First of all, it's a complex calculation, and it's added in the post-processing phase of FEM-Design. So post-processing phase is the phase where the equations have been solved and the unit load vector have been traveling on the bridge, and the analysis is being made in this stage. It doesn't have any contribution to nonlinear FEA, but it is possible to run a nonlinear calculation by generating a discrete load case and then solving the equation system. So the traffic load envelope in a finite element node is based on the influence graph. So for every node, an influence graph is being generated, and based on the influence graph, the software will search for the optimum or the worst load position in this case. It's an object in the model space of FEM-Design. It's added to the load case. So it is actually a load case in the model, and it is coupled with moving loads. And moving loads was an old feature that have existed for many years. And for those of you who are familiar with moving loads, this is repetition, but for those of you who is not familiar with it, it's basically a moving load, a discrete moving load. And in this case, the equation system and the finite element solver is being performed for every discrete load case. Advantages, it's already implemented in FEM-Design. It's been there for many years. It can provide us with the influence graphs, and it's very easy to understand. There are, however, some disadvantages. It's almost impossible to use as a direct input for design because it requires very many load combinations and load cases. And also it could not handle variable load systems or arbitrary regions of load system. So for example, the uniformly distributed load in LM1 needs to be placed in the most unfavorable position in both longitudinally and transversely with respect to the influence graph. So the conclusion was to not continue with this, but it is a great springboard, and we've also coupled it with the traffic load envelope. Some background about the development of bridge applications in FEM-Design. It started many years ago, even before I started at the company. And initially, of course, it was the moving load feature, and it's been there. But during the phase, we've added features regarding post-tension, construction stages, and also handling of load groups. And now finally, sealing the deal and the package, the traffic load pattern, which was the final cherry on the cake. And of course, kudos to our software developers who have been doing all this work for many years, and Attila in specific, very enthusiastic and an excellent developer. There was a small estimate of 75 hours, but we can assure you it took longer than that to develop this feature. But now it's finally here. Okay, so what can you do with it? As you know, the LM1 in Eurocode, it has a tandem system and a uniformly distributed load. And this load model needs to be placed arbitrary in order to maximize or minimize a specific result. For example, the bending moment in the longitudinal direction. And in Sweden, we have our own national dependent parameters, and in Denmark, you have your own. So I've been creating different scenarios of this load model, and we will look at them together. And what we get as a result is basically a traffic load envelope. So what we are looking at on the top is a specific load model from the Swedish National Annex, a specific vehicle. And in the top, we are looking at the shell internal forces and the bending moment in the bottom of the shell. So we only see values from 0 to positive infinite. That's the result domain. And in the other one, we have results from 0 to negative infinite. That's the result domain for the upper fiber. But of course, this feature can be used for arbitrary structures. So for example, this is a garage deck with beams. And so based on one specific point's influence graph, the load pattern should be unique for every point. So in this case, we are maximizing the bending moment of the shell in mx minus. And for every point I'm hovering, I get a discrete load case generating this specific value. But all these load patterns have not been solved in a classical FE manner. It's solved in the post-processing phase. And I will show you what the difference is. Here are a few of the norms currently implemented. So the Eurocode and some of the Swedish national vehicles, but of course the Danish vehicles could easily be implemented as well. And how to handle the different systems, considering braking forces and centrifugal, is also very important, and I will show you how that can be done in the software. And as you know, it's called the multi-component actions in Eurocode. Just showing some realistic load cases on the top right. The LM1 can give us quite fun load patterns, and they can look a bit made up, but as you know, if there's a collision in one lane, traffic is being stalked in the bottom, you have a floating traffic on the other side, you can get these loading scenarios, which kind of looks mathematically possible, but there are of course real case scenarios when the traffic, a collision happens, and the traffic needs to be redirected or something. And as I mentioned before, the load, the UDL, should only be applied in the unfavorable parts of the influence surface, both longitudinally and transversely, which makes this problem a bit more difficult. Okay, so the theory, we've implemented the Eurocode load models, we've implemented specific special vehicles, we can assist the multiple lane alignment, and we can show the maximal value and the related simultaneous results. We can also generate this particular, for every particular FE node, we can generate the load system that gave that specific value. And that load system is possible to rerun in a classical FE manner. We can handle arbitrary 3D geometry with inclined surfaces, of course not the vertical surface, but real case geometries. And we've handled some assistant tools to make this work procedure quite convenient as well. So the algorithm itself, it's a 3-step procedure. First, we generate the influence graph, and that's being done by simulating a unit moving load on the structure. Based on the influence graph, the post-processing result set calculation phase starts. And for all lane alignments, for all permutation, transversal steps, etc., the software is working. And then if you want, you can also calculate the simultaneous load effects. We can handle surface areas as wheels, so we can make the wheels bigger, and we can also integrate the influence graph in a transversal direction. So when we have a positive and negative for one lane, we can get an average of it. And as you see in this example to the bottom right, here we allow the load to be placed exactly according to the influence surface, but we can also limit that if we want. And we've implemented 2 search algorithms, one discrete and one continuous. And the discrete search algorithm is based on how many points the cost function which we create in the end has. So based on how many points we want to evaluate on the cost function, we found a maximum or a minimum, and this in fact will become the result. But then we've also implemented a continuous search algorithm which tends to find the exact theoretical solution, but of course with the cost of not always finding the optimum solution. So we have these two different possibilities. I got a comment when visiting a client that this is an amoeba search, like how a virus is being spread, the continuous search algorithm, that it has some similarities with it, but I've not studied that topic any further after she mentioned that. But here are two cases which in theory has a trivial solution. So we're trying to find the maximum bending moment in the top of a two-span beam. And of course, we know by looking at the influence graph that the software should place them on minus 1.92 in the left span and minus 192 in the right span. So for the multi-start optimization, it actually does. It finds the theoretical value. But for the brute force, we will see what the software does. It will place it slightly to the right. Let's see if we get it. There we see it. So we have a slightly shift. However, the value doesn't differ that much, but it doesn't tend to find the theoretical solution if you have a simple problem. And worth mentioning some limitations. So the stakeout line for the traffic is not allowed to intersect itself in the top plane. So a spiral going like this and seeing from the top intersecting itself is not possible. Also, we have a possibility to do a simple line model. So if you just want to do a 2D evaluation for like a unit strip or something, but in those cases, we don't have a torsional influence graph currently, but this is something we could develop further. So how can you use it? It's a three-step procedure. First, you define the traffic load cases. Then we need to arrange and couple the traffic load cases in load groups. And then finally, running the max of load group calculations. So we will not look at these examples too much. You could have a look at this example. This is an end shield bridge, which we will look briefly on later. But I hope during this presentation that you found some questions, because then we will continue with some FEM-Design live demos. So if there is anything particular you want us to show, please let us know. Otherwise, I will freestyle, of course. So this is an example of looking at the LM1 for this bridge. And I only have two tandem systems because it's the Swedish national dependent parameters. We don't include all three tandem systems. And here I'll be looking at the bending moment by taking a graph in the model. And then we have some special vehicles in Sweden, which we will look at as well. And here you see the UDL, the uniformly distributed load is constant 3 meters for every lane, which is one of the limitations we have in Sweden. So these two load models differ quite a lot. And then we can take out the results to evaluate them in Excel, for example, to see which one of the load models is governing. And then we can get the design forces with the torsional moment as well for shells. And we can also see the load combination generating the most severe results. We have some training materials for this as well, and let us know. We have all the video content on our YouTube channels as well that you can study by yourself and get started with the module. Okay, so if we haven't gotten any question, Anders, I will continue by going into FEM-Design.
There is one question, Joe.
Okay.
If we can handle curved bridges.
Let's see. I will just make it a bit larger. Kan programmet hantera curved bridges? Geometry, kan programmet hantera buer? Is that curved?
Yeah, like an arch.
Okay. Yeah, I mean, I have a pretty nice example actually. Let's say this is a curved bridge. But you have to be quite used to our API. I mean, okay, you can do it all in FEM-Design, but it will be quite cumbersome to make this geometry in our software. But if you have some knowledge in Grasshopper or Rhino, for example, you could generate these, let's say, curved geometries, but you can also work with arches. But we then can discretize it to plane objects, and so all objects in this model is a plane triangular shell, let's say. We can mesh it, and we can here I'm also actually using the new virtual bar tool, which is quite nice. So I'm looking at all the result in the center line with the virtual bar tool. So I'm looking at the beam kind of behavior instead of looking at the shell internal forces. So yeah, this is possible as well. Of course, it requires some more knowledge in the software, obviously, to deal with these kind of structures. But for beams, we can work with the curved object as well. But for shells, we only have plain facet shell elements. But of course, we can approximate the geometry quite well, and to make a model like this as well. I hope that was a good answer to that question. Okay, so we will enter the software and I will show you live how it looks. So now I'm choosing the Swedish National Annex. And I will create a geometry. And I will make a shell which is 12 by 12. And I will apply a line support group, and I will clamp it on these two sides. So we will enter the load tab. And we have the new group, the traffic load. And we have the moving load next to it. And as I said, these two are coupled, meaning that when I generate the traffic load, something will happen in the moving load as well. So we have the two options, either working with a carriageway or a simple line model. I will choose the carriageway. And then I can pick my existing region. And I need to define a stakeout line for the traffic. So in this case, I will do a straight line. Then I will enter this dialog box. And there is a nice question mark here, which will take you to the wiki page. And here you can read more about the different kind of options. So we will call this load model 1, the tandem system plus UDL. And I want to optimize or find the worst mx plus in this model. So I'm only interested in mx plus, and I want to find the simultaneous results as well. Then I enter the load model, and in Sweden it looks like this, but I will use the Danish load model if I've interpreted correctly. I entered your national annex, and I could see that the alpha parameter for the lanes should be 1, and the alpha parameter for the UDL should be 0.67 for the first lane only, and then 1 in the rest. So if I'm not completely off, we'll write it like this. So the vehicles is actually created in a new library, which looks like this. So the LM1 tandem system, lane 1, has an axle load of 300 kilonewton. It has a wheel spacing, a wheel size in 2 directions. And if you want, you can create larger wheel areas. If you don't, maybe if you have some kind of fill for the bridge and it's being spread in some kind of angle. But I will choose this, and then we have the UDL, which is 9 kilopascal, and this one, which is 2.5. So these are the factors, and in Denmark I'm applying this 0.67. There are some load multipliers, but in LM1 they're not needed according to Eurocode. And then the lane alignment. So I will fill a lane alignment on this bridge, and since it's 12 meters evenly divided by 3, I will have 4 lanes. And I have 2 different search algorithms. I will choose the multi-start. Then I get this pretty load figure. What I will do is to show the different proportionalities. So graphically, the software will show this specific load case like this, but it will alter the major tandem axis, the major tandem system in all the lanes. So it will check the different scenarios, and we will see that. But don't forget that I said that it is coupled to the moving load icon. So what the software does is it is creating these unit loads on the bridge, generating the influence graph. And if you think that the intensity is too high, you can of course play with it and make it more coarse. And then of course generate some kind of finite element mesh. And then we will run the load case calculation. Okay, I will just pause here for a minute. So the load pattern calculation, post-processing phase, calculating influence lines and surfaces, calculating parameter sets, and then the simultaneous results. And this is the algorithm. So the intensity of the influence graph, the search algorithm choice can affect these calculations, and if we want, we can deactivate the simultaneous results. Okay. So I will enter the shell internal force, show the color palette, and let's look at it in this way. So because I only requested the positive values, the result domain goes from 0 to positive infinite. From 0 to positive infinite. I will create a body, which is the upper, and then I will use the wizard. So I will not redo the procedure because I want to use the same influence graph. I want to use the same influence graph, but I want to request a negative. Some negative ones. And there it is. Okay, so if we press this new icon, we can generate the load case that gave us the result. So if you are standing in this point, the software can show us immediately which load position is giving us this value. So this value, for example, it's due to this position. And why does it look like that? Then we need to generate the influence graph. So I'll create a new window, arrange. So we see that for this point, it has placed the load there to get the maximum negative. It was not actually that point, it was, let's see if we can enter a result point. Okay, I have a quite small number there. Let's look at the positive instead. And we have this load position. And what we can do, we can generate this particular load position. And here we can run the calculation in a classical FE manner by solving the equation systems. Okay, I will show you some other examples, more realistic, let's say, bridges. So this is a quite classical bridge in the Nordics, at least in Sweden. And what we do here is that we start by creating the load groups. So the dead loads, any kind of earth pressure, the support motions, if we have any surcharge, and then we generate the traffic loads. So in Sweden, we add our specific vehicles, but we also have the Eurocode loads, LM1, LM2. And then we group them in the setup here. So we couple the vertical loads with the braking forces and the lateral forces. And we have some results for the LM2 as well, and the type vehicles. So what we end up with is several load patterns. So we need one discrete load pattern for positive, negative, etc. So in this one, for example, we should be able to find the MX plus there. So this one only has the MX plus result. And we can create several lane alignments. For example, a left-oriented and a right-oriented. And then we run the load case and maxF load groups. And we get the design envelopes. So for example, if you want to look at the MX plus, we can see that for this point, oops, we get this load pattern. So we can actually see the load patterns in the design envelopes as well. So for example, if it alters between some specific vehicle you have in Denmark, or if it enters the LM1 in Eurocode. And if you're probably familiar with the concrete module as well, we can get the effects including the wood armor effect as well. So for example, here we have the MX and the MXY, and then we can get the wood armor effect. So you can follow your design from the structural analysis to the design forces with concrete design in FEM-Design as well. So I have just one more example I would like to show, which is a slightly more complex bridge, several spans. And here I've been simulating several traffic loads. So for my design envelopes, I kind of do not know which one will give me the worst load pattern. So here I can see all the different results. Just need to find the node. So here, for example, LM1. And if I go to another position, LM1 is being placed there. But if I, for example, go to the MX minus, and I do the same thing, it jumps to another load pattern, which is governed from another load model. And we can get these results to quality assure all the results we get in FEM-Design. Okay, so I will stop here. I think we need some time to answer questions as well. And hopefully there are a few questions.
No questions yet.
Oh.
Shaho, are you finished with your presentation here?
Yeah, I'm not gonna show anymore, so you can stop recording.
Yeah, and we'll leave the webinar open for 5 more minutes, and if there are no questions, then that's it for today then. Jeg håber det kan bruges. Jeg håber I kunne lide det I så alle sammen. Vi hører selvfølgelig også meget gerne fra jer, hvis I har nogle kommentarer til det.
Nice, we got a question, Anders. Can you define a cross section and check the capacity? You mean, for example, if it's a steel section, I assume, or maybe you can, because if it's concrete, we can design the reinforcement, of course, but if it's steel, we can check the capacity of it. But then we need to enter the design modules, and the design modules are either concrete, steel, or timber. So if it is a steel section, we can generate the structural analysis, we find the sectional forces. Based on the sectional forces, we get the design envelopes. And for traffic, it's the max load group. So for example, MX plus, here we get the maximum bending moment with the simultaneous load effects as well. So in this specific point, whoops, we have this governing load combination giving us 535 kilonewton meters per meter, and then we get the simultaneous load effects. And as you see, we get the torsional bending, which needs to be added considering the wood armor for the design of the reinforcement. So if we go to concrete and we check the required reinforcement somewhere in this region, the program is calculating the required reinforcement based on the design forces. So instead of 523, becomes 692, which gives you a specific required reinforcement in that point. So we will visualize that just in a sec. So we get 3476 millimeters square per meter. And we can also apply that reinforcement in that specific point to verify that it's enough. And then we can use the auto design based on some specific parameters and reinforcement. We apply the reinforcement in that specific point or in that specific shell object. And then the program has added a bit more than the required one. And as you see, it has applied the same ratio in all this region. But of course, if it's steel, we can check the capacity of the given section. Okay, we got one more questions. We got a very good question actually. And someone is asking if there is a simple control we could use to validate the 3D bridge modules. And we have the simple line calculation, which is very elegant. And there is the limitation that it cannot handle torsion, but to find the bending moment in the longitudinal direction, it's very good. And I will show you one example of it. So I will generate a beam object. Some kind of unit strip, so 50 centimeter high, 1 meter wide. Concrete material. Okay, so it's some kind of continuous beam. We will amplify the supports a bit. Maybe 3. And we will use the simple line model. And we will run. And here we can take the LM1 tandem plus UDL. And we only request the bar internal forces. We choose the Danish load model, 0.67. And here we need to set up the lane alignment. And the lane alignment is a 3D lane alignment. But if it's a simple line model, all the loads will be lumped to one point. So if we say that we have 2 lanes, it will be the 2 tandem systems will be applied. But let's just work with 1 tandem. So we say that we have 1 lane, which is 3 meter, and it's centric over this unit strip. Then we get this load case. And for the beams, it's very important to set a proper division number. And we can always play with the discretization of the influence graph. Let's take 100. And then we get the results, and we can see that, let's amplify the point loads a bit so we just see them clearly. We can see that for every point there is a discrete load pattern. And this is due to the fact that the influence graph looks like it does. So for example, maximizing the positive bending moment in this point, then we need to place the load either there or there. And if we look what the software does, this is exactly what it did. So the simple line model is very good, but we need to know that, for example, the result it generates is in fact, it can be several point loads if you have a wide bridge. And a wide bridge means several lanes. So if I would apply -3 and then L2, and I would rerun this, then we actually have 2 loads in this point. So we need to consider that effect when we have a simple line model.